Okay, let's talk about the limits. Limits are the most essential and important part of Calculus 1. So pretty much all of the calculus is built on the limits. I will explain it to you later, but let's talk about what limit is. So limit asks a question. What value does a function get closer to as x approaching a certain point? Let me show you an example with a graph. I have to plot the graph first. So this is going to be our y-axis, and this is going to be our x-axis. It doesn't look perfect, but it shouldn't. Definitely. Make sure to label all of your axes. This is x, this is y. And let's consider the function f of x equals 1 over x. It should look something like this. Oh my god, it looks horrible. Those lines. Yeah, you can plot it in you can plug it in a Desmos and you'll see the exactly same thing. Okay, so when you approach a function from the left, the negative side, on the right, you see that at this point over here, the x value is pretty steady, but then it suddenly drops down. But the thing is, it never approaches 0. The same thing on the right side. It's just like mirrored thing, right? It's pretty symmetrical. If you're going to approach 0 from the positive side, like this, still goes steady, 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 and it goes up suddenly. So this function over here is 1 over x. And you have to keep in mind that this part that goes down and this part that goes up, they never really intersect. In the perfect world, they would intersect when x equals 0, therefore in our function would be 1 divided by 0. But we know we cannot divide by 0. So what do we do in this case? In this case, we have to write down the limit of x approaching 0, 1 over x. And we have to take a look where it's even located. Well, I mean, when you're looking for the limit, it's gonna be in it's going to be y value. It's going to be f of x, right? F of 0, let's say, right? So we cannot really directly take the 0 and plug in over here and find the value. So what we can do, we can consider the function from each side. So in order to mark it, we have to write down the limit of x negative approaching 0, 1 over x, and x positive approaching 0, 1 over x. So this part over here is going to be from left to the right. This part on the bottom is going to be from right to the left. And since we cannot really directly plug in 0, we can try to plug in the value that is going to be pretty close. Let's say 0.1. It's not the closest value, but it's closer than 1, right? If we would plug in 0.1, we're going to get 10, right? So when our value of x is located at 1, let's say this is 1, our y value is going to be 10. Then let's try to plug in even the smaller number. 1 over 0.01. It's going to give us 100. So when our x is located at 0.01, our y value is 100. Let's say this is our 0.01 and this is our 100 on the y-axis. Let's take a look at this part. It's going to be on negative side, approaching from the negative side. Same thing, if we plug in 0.1, let's say, actually in this case we have to plug in negative 0.1 because we cannot really plug it in over here. Because we go from the left side, which is negative, right? If we divide it, we'll get negative 10. Therefore, when our x value is negative 0.1, our y value is going to be -10. So if this is -1, over here, it's going to be -10. And if you would try it out, you can plug 0.1, 0.01, 0.00000001, and the number will just get higher, higher, higher. It's going to be 10, 100, 1,000, 10,000, and etc. So we can find a pattern here. We see the pattern that the number constantly increases, increases, increases with every single decimal added in our value, x value, right? So it means that this number goes to infinity. It just never stops. Every single time you add the decimal, every single time you add additional decimal for the x value, it's gonna get higher and higher and higher. Therefore, on the left part, as we can see, it goes down and it gives us negative infinity. On the right side, it's quite the opposite. It goes up and it's approaching, approaching, approaching 0. It never gets to that 0, but it's approaching. Therefore, it's going to be a positive infinity, right? And let me show you a real example. Let me just erase this stuff over here. So you could have an idea of the limit. I want to give you a real life example. Imagine this is mountain, right? We're standing right over here. Let's say it's a canyon or a mountain, it doesn't matter. This is you over here. And this is your friend standing here. And he's waiting for you to come on his side. But let's try to apply some critical thinking. It's not that easy because you cannot just go straight like this because you would just fall and die. Either you get stuck there or you fall and die, right? You can take a step on the right. Oh my god, his head disappeared. You can take one step on the right. You can take a second step on the right. You can take the third step on the right. You can take infinite amount of steps on the right depending on their size, as long as you're not reaching this point. This is going to be your limit over here. This is the point that you cannot reach, and you will reach it at negative infinity. Okay. Now let's get to the actual practice. Let's try to solve the real problem. So it's asking us to find a limit. On the right side, I drew the actual graph. It looks like this. It kind of looks like linear function. I mean, it is pretty much, but it has an exception. You see this hole over here? This is our limit. So if we would try to plug in 2 in this part, in this fraction, it would give us an error. Why? Let me show you why. Because when you plug in 2, it gives us 0 on top and 0 on the bottom, and you cannot divide by 0, unfortunately. In the perfect world, maybe you could, but not in ours. So we have to do some algebra here. It's not that difficult. So we have limit of x approaching 2. We see the difference of squares, and we apply it. X minus 2, x plus 2 in our numerator, and x minus 2 in our denominator. So we can cancel these out, and we just have the limit of x approaching 2, x plus 2, and if we would plug 2 over here, it would give us 4, right? Makes sense. And we can take a look at our graph now. If we go one step and second step on the right, and we go 4 steps up, 1, 2, 3, 4, we can conclude that our limit is located at x2 and y4, right? So this is our limit over here, 2, 4. Okay, let's proceed to the next problem. Okay, here we don't really have the exact function. I would say continuous function. You can already see that it's not continuous. Let me just erase this thing first. Okay, so it was clear. So on the left side, we see f of x equals 1, where x is less than 0, this part. And on the right side, f of x equals 2, when x is either equal or greater than 0. So in this case, if we would try to take the limit of, as x approaches 0, of f of x, we can't really do much. We have to consider the left side first. Limit of x negative approaching 0, f of x equals 1, right? So we do not have any x's in our function, so there is nothing to plug in. No, it doesn't matter what kind of value you're going to plug in, it's still going to be 1. So it means that this part is approaching value of 1 that is located right over here, right? And on the right side, it's going to be limit of x positive approaching 0, f of x equals 2. Same problem over here. We cannot plug in any single x value, therefore it's just approaching 2 no matter what. And what can we conclude? We can conclude that they are meeting at the different y points. And when you have this problem, it means that your function is not continuous, therefore limit does not exist. Just keep in mind. Okay, the importance of limits in calculus. As I mentioned before, the whole calculus 1 is built on the limits, right? But why? Let me give you an example. We have to revise the average rate of change first. As you remember, in order to find the average rate of change, which is pretty much the slope, we have this formula delta y over delta x. We can also rewrite it as f b minus fa over b minus a. Right? The b is going to be the final point, and a is going to be the initial point. So it's like x final, x initial. Right? Let's take a look at this graph over here. Imagine you have this function. Let's say it goes this way. Make sure to label axis. And you want to find the average rate of change between 2 points, right? You have the, let's say this is 1, this is 2, this is 3, this is 4. Let's say this is going to be 6. This is going to be 18. This is going to be 30, right? Just an example. So when we have x2, our y is 6, right? This is where they intersect. When we have our x equaling 4, our y equals 30. So when we want to find the average rate of change, or so-called slope, we would just plug in those values. It's going to be, for denominator, 4 minus 2. For numerator, it's going to be 30 minus 6. Which results into 24 divided by 2, and it equals 12. It means that our average rate of change for this function is going to be 12. But what if we would want to find the instantaneous rate of change? This is where the limit comes in handy. The instantaneous rate of change is where you don't need specifically 2 points to find the rate of change. You can just apply 1 point. But you would ask, how can you do that? Because when you're trying to find the average rate of change or some kind of rate of change, you need 2 points. And when you would have only 1 point, it means that your x final and x initial would be the same point. Let's say it's going to be 6, and you have a 6 minus 6 in the denominator, which will result into 0, and you cannot divide by 0. So in this case, we need to use the limit. So first of all, I would like to write down delta y over delta x equals y final minus y initial, and x final minus x initial. And we know delta x equals x final minus x initial. And we can add x initial on two sides. And our x final now equals x plus x initial plus delta x, right? And I will show you why I did it. So when we would try to plug this inside of our rate of change formula, as we know, y final is pretty much f of x final, and our y initial is f of x initial. Let's try to do that. We have f. So this is our x final. It's exactly the same thing as x initial plus delta x. We can plug it in over here. X initial, let's write x initial as just x. So there was no extra work. X plus delta x minus x initial. Our x initial is just x, so it's minus f of x over x final minus x initial on the bottom, which is just delta x. And when we're looking for instantaneous rate of change, we know that delta x has to result into 0, because when you take a number of 6 and you subtract 6, it's just 0, right? So since we can't directly write it this way, let me just erase this stuff. We don't need that anymore. So if we would just try to plug the 0 there, it's not going to result into anything. It's just going to give us error. So this is wrong. It means that we have to take the limit of delta x approaching 0, and now we can write it as f of x plus delta x minus f of x over delta x, right? Perfect. And this exactly the formula for instantaneous rate of change. Some people write it with the variable of h approaching 0. It does not really matter. This is actually the formula notation that you will see more often than the one that I showed you with delta x. I just wanted to give you the clear explanation where this formula comes from scratch, so you could understand how it works, not only try to memorize the formula. I think this is a better way of understanding the material. So yeah, and if we would try to plug in a certain function, let me just erase this stuff here. If we would try to plug in a certain function, let's say we have a function of f of x equals x squared. We can try to give it a shot. So if our f of x equals x squared, and our f of x plus h has to equal to x plus h squared, and this is just is square addition, so we can write it down as x squared plus 2xh plus h squared, right? This is our f of x, this is our f of x plus h squared, and let's just plug it in this formula. So the first part, f of x plus h, x squared plus 2xh plus h squared, we just gotta subtract this part, which is x squared. We just keep h on the bottom as it is. Make sure to add that limit on the left side all the time, or otherwise you'll get all of your points subtracted. Now we can cancel out our x squared, right? So we're left with the limit itself and 2xh plus h squared over h. What we can do over here, we can definitely factor out h. Let's do that. So h, 2x plus h over h. We can now cancel these out, and we have limit of h approaching 0 to x plus h. And at this point, we can confidently plug in 0 because it's not going to result into a 0 in denominator, which will give us an error. So we just plug in 0 over here, and it turns into 2x. So this is the most essential formula for finding a derivative in calculus. I just wanted to give you a little introduction here. And let's proceed to the first problem. It's already solved. Okay, let me just erase that. And I will show you. As limit approaching x approaching 3 for the function 2x plus 1, we know that if we plug in 3 directly, it's not going to give us a division by 0. Therefore, we can just confidently plug it in. So 2, 3 plus 1 equals 6 plus 1, and it equals 7. Right? Perfect. That is our final answer. No extra work to do. The next example, I think I solved it as well. Let me just erase that and we'll start over. Okay. In this case, we have a limit as x approaches 0. In numerator, we have square root of x plus 1 minus 1 over x. If we try to plug in the 0 directly here, it's going to give us division by 0. We can't do that. This is the rule number 1 when you're solving limits. So we have a square root of x plus 1, and we would try to solve it directly. It's going to look a little messy. So I personally really like to substitute it with some certain variable. Let's say let square root of x plus 1 equal n. Yeah, it works. So now it turns into limit of x approaching 0 n minus 1 over x. In order to resolve this problem, we can actually multiply the top and the bottom part by n plus 1. And it will allow us to apply the formula, which is the difference of squares. N minus 1 multiplied by n plus 1 gives us limit of x approaching 0, n squared minus 1 squared. I actually forgot that minus 1 over here. Yeah, is this one? No, I did not forget it. Everything's cool. We have x of multiplied by n plus 1 in our denominator. And at this point, we can actually go back to our initial square root of x plus 1, since this part over here is squared, and it just turns into x plus 1. So in our numerator, we'll have x plus 1 minus 1, because minus 1 squared is just 1, right? So we just cancel these out. On the bottom, we have x n plus 1. We can cancel out our x's, and it gives us limit of x approaching 0, 1 over n plus 1. Actually, I forgot to change n, so let's do it one more time. It's fine. So since we swapped our function a little bit, it looks a little bit different now. So when we would try to plug in our 0 for this function, it's not going to result into division by 0. Therefore, if we plug 0 over here, we'll have a square root of 1, which is just 1. And it results into 1 over 1 plus 1. The answer is 1 over 2. Yeah, it's a pretty tricky problem, but as long as you understand what you're doing, you know algebra well, it's very easy to solve. Okay, this is the same exact problem. It was solved already. Okay, let's take a look at the function which represents x squared when x is less than 1, and 2x plus 1 when x is equals or greater than 1. I would try to draw it first. Let me use the straight line for this. There we go. So let's draw the left part with the red color. And x squared is just a parabola, right? So we can just draw it this way. Let's say it stops right here. This is where our, let me label the axis. This is where our x equals 1. It goes on 2, 3, 4, and etc. And this part is going to be green color. Two x plus 1. If we would try to plug 1 in this example, if we plug in 1 in x squared, it gives us 1. Therefore, we also have 1 over here. This is where it intersects, right? And for the 2x plus 1, if we would plug in 1, it's going to give us actually 3, because 2 multiplied by 1 is just 2, and 2 plus 1 is 3. Therefore, it starts somewhere right over here. 1, 2, 3. And it goes somewhere right there. So what can we conclude just by looking at this graph over here? Since the function is not continuous, limit does not exist. That is it. Those are very simple rules about the limits that you have to know. It will allow you to solve all of the limit problems in Calculus 1. Okay, thank you very much for watching this video. I wish you good luck.